My name is Alper. I am a PhD student at Singapore University of Technology and Design. Today, I am going to present our recent work on the edge obstacle surmounting method using hybrid locomotion. Mobile robots are vital for unsafe environments like disaster sites and hazardous areas where human presence is undesired. These areas are one of the most challenging terrains to traverse, where many obstacles with different types of surfaces exist. Thus, robots navigating such environments require a high degree of maneuverability and agility. Obstacle climbing is an important indicator of these criteria and provides insight into a robot's full potential.
There are several challenging problems in obstacle climbing. Robots need to increase their maneuverability and mobility depending on the task. One strategy often observed in caterpillars is the exploitation of large deformations and therefore nonlinearities to increase reachability. Non-parallel surfaces present another challenge for robots. Transitioning between those surfaces requires several joints, actuators, and complex control systems. Finally, robots need high adhesion between contact surfaces to achieve desired locomotion. Several mobile robots have been introduced with different surmounting methods. Transformable mechanisms allow robots to reliably switch between locomotion modes based on the given task. However, these mechanisms require extra actuators to be installed, which increases weight and energy consumption. Trigger mechanism robots transition between legged and wheel locomotion when the force exerted on the locomotion mechanisms exceed a certain threshold. These robots mainly use radial expansion, which is easy to achieve, but the driving and transferring forces are mixed due to the same circumferential rotation. Next type of robots have rimless wheels and move merely by spokes. The spokes help the robots climb obstacles like legged robots do, but unlike their complex control systems, they offer simplified structure. However, they sacrifice the stability and maneuverability of the traditional wheeled robots. Passive mechanisms utilize their novel kinematics to increase surmounting capabilities. But this approach generally requires additional joints and structures, which increases the complexity and weight of the robot.
A robot can perform a task in a given environment using quasi-static methods if geometric constraints are satisfied. This is referred as quasi-static matching condition. In obstacle climbing, this condition is satisfied if the obstacle height less than or equal to the robot's longest radial workspace length. Then, the robot can surmount the obstacle quasi-statically. Similarly, the quasi-static condition will fail if the obstacle is higher than the robot's longest radial workspace length. Then, the robot cannot surmount the obstacle quasi-statically. On the edge, a surmounting method utilizes the robot's body and uses it as a contact point in quasi-static mismatch condition. The center of gravity of the robot is moved into the support polygon generated by the end effectors of the front legs and line of contact with the bottom of the robot's body. Since static stability is achieved, rear legs can be raised from the ground and the robot can recover on the tread, completing surmounting. This proposed method requires using both legged and wheel locomotion concurrently. Thus, a hybrid robot is needed. QuadRunner is a transformable quasi-wheel quadruped, where its novel 5-bar leg design allows it to transform between wheel and leg locomotion seamlessly. Each leg has a 2 degrees of freedom and control with virtual leg parameters, theta and gamma. QuadRunner uses one laser rangefinder to measure distance of the obstacle, which is installed in front of the robot. Thanks to the unique leg design of QuadRunner, the robot's surmount motion can be modeled using 2 different kinematic chains, namely a 4-bar linkage and a slider crank linkage. In 4-bar configuration, rear legs and edge of the front quarter circles act as pivot point. In slider crank configuration, Rear legs act as pivot point, while front legs can slide in either X or Y axis using wheel locomotion. Using the kinematic equations of these linkages, desired trajectory of the center of the gravity can be achieved. Obstacle climbing state is expanded into 5 substates, where operations are executed from left to right in order. Substates is denoted as their initial letters, and each substate has a unique color code to differentiate them in diagrams. Each substate will be explained separately. The surmounting process begins with the robot walking towards the obstacle until it reaches the desired gap between its front legs and the obstacle. Then, the final gap is closed with the front push maneuver, which provides enough traction between the robot and riser. In hook substate, the robot acts as a slider crank and the front legs climb upwards. Then, using QuadRunner's novel leg design, front legs transform into a hook shape, which allows transition between orthogonal surfaces, riser and tread. Lastly, rear legs are recovered to overcome kinematic constraints by slipping them. In the beginning of the 4-bar substate, the robot actuates as 4-bar mechanism as described previously. Then, recovery phase is performed, and at the end of this substate, the robot is configured as slider crank mechanism. For slide substate, the slider crank mechanism behavior is performed twice, with a recovery phase in between. In this substate, robot body used as contact point, and it is touching to the tread at the end. It should be noted that COG of the robot is supported by the contact points on the tread, allowing the rear legs to move freely. The robot's recovery on the tread starts with front legs rotation, which reduces the pitch angle of the body. Next, rear legs lifted off from the ground and put on the tread. Finally, QuadRunner moves forward and recovers to stance mode, which completes the surmounting method.
Described substates have been shown together in this experiment, where the obstacle height is 22 centimeters. While approaching the obstacle, QuadRunner's stance height is 17 centimeters. On the edge surmounting process takes about 23 seconds to complete.
Obstacle height for on the edge surmounting method is limited when the robot body is in contact with the tread. Based on geometrical constraints, QuadRunner can climb obstacle of heights between 7 and 22 centimeters. However, the hook substate requires the obstacle to be longer or equal than the radius of the wheel. In our case, radius r is 10 centimeters. There are 3 separate contact surfaces in the environment, and friction requirements must be satisfied to successfully surmount the obstacle. During climbing, QuadRunner contacts either ground and riser surfaces or riser and tread surfaces. Thus, these surfaces are not independent. Using the static equilibrium equation, 2 contact configurations can be combined. Here, green area represents the necessary friction values for each contact configuration. For the experiment, wooden plates are used, and their friction values were experimentally found as 0.8. There can be cases where friction requirements are satisfied, but motors are not powerful enough to move the robot to desired position. Thus, torque analysis needed. Using the coupled free body diagram of the QuadRunner, necessary torque values are found. The maximum required torque value is 1.26 Newton meters, which can be provided by QuadRunner's actuators.
Here, we tested the reliability of our surmounting method with different obstacle heights. 7 out of 10 experiments with 22 centimeter obstacle height resulted with success. If the robot doesn't approach to the obstacle orthogonally, it fails to climb the obstacle. This problem can be solved by adding multiple distance sensors and rotate the robot before the climbing process. Our future work will include onboard obstacle detection, object manipulation using claw mechanism, and hybrid locomotion where legged and wheel locomotion exists concurrently.
Finally, this graph shows the trajectory of the COG of the robot while surmounting 22 centimeter obstacle. Thank you.